Hello, everyone. So today we're going to talk about naming. And naming isn't really about naming. So this is in chapter 2. And the truth is, I don't really care about naming. But we're going to do a lot of naming and we're going to learn how to name things. And that's because naming really is a way for us to demonstrate that we've learned and to kind of learn the system of how you put compounds together and a little bit about bonding. And so the little bit of chemistry that we need to know in chapter 2 to be able to get started with sort of the rest of Gen Chem. So things like what ions do different elements form? What's the charge on the ion? Are is this compound ionic or covalent? Um, and what charges transition metals might have and how you put a compound together and some of the polyatomic ions and things like that. So the naming, yeah, we're going to do a lot of naming. There's a homework assignment on WebAssign where I've got literally hundreds of compounds that I typed in, and you get random ones each time and try them in practice and until you master the naming system. And once you've mastered the naming system, then you will know that little bit of chemistry that's important to know to move forward. What ions, different groups form, how to put ionic compounds together, um, and stuff like that. So it's really important to be able to do this. I'm not going to count things wrong if something's misspelled or a letter's mistaken or something.
The computer WebAssign, of course, will. But when it comes to, on a test or something like that, if you spell phosphorus incorrectly, I'm not going to have two choices, one where it's spelled correctly and one where it's, spelled incorrectly. Um, that's not what we're about here. It's learning the chemistry that you need to know in order to put the compounds together. So that's my little introduction to naming. And and so the naming in chapter 2 too is a little bit of our introduction to bonding and compounds and how elements come together to form compounds. So that's why it's there. There's a couple of chapters on bonding later in the semester, and there's a whole chapter on periodic table where we'll review some of that again. But for right now, it's just a few things that we have to know. And so here we go with naming, and I'll do a bunch of examples, and hopefully the examples will help and make sense that you can do that homework. So chemical compounds. So compounds are just, elements combined to form pure substances. So what are some examples of a compound? Well, sodium chloride. I put too much on my tomatoes tonight. Gonna have high blood pressure. Water, two hydrogens and an oxygen. Hydrogen peroxide, two hydrogens and two oxygens. And the common name, your book has a whole bunch of stuff on common naming system. We're not going to do any of that. It does not matter to me at all if you know ferric, ferrous, phosphite, all those different ones. Okay, I just there's no reason for us to have to know the common names. Whatever ones you pick up, uh, just from doing chemistry and you remember them, fine. But there's no reason to memorize a bunch of that stuff. It's just the systematic naming that we're going to do because it's really about the system of naming. So in bonding, we have two types of bonding. Covalent bonding, where electrons are shared between the nuclei of atoms in the bond. And then ionic bonding, where ions are just attracted to each other by Coulombic forces. That means the attraction between positive and negative charges. So that's our two types of compounds. But these are really, really different. So covalent compounds, those form molecules. So a molecule is something like water where it acts as one unit, H2O, or hydrogen peroxide, H2O2. Those things are
one unit when they form a molecule. And so you have a glass of water, it's a bunch of H2Os all in the beaker of water, in the glass of water. Ionic bonding is not like that. They're not molecules. So sodium chloride is not one sodium chemically bonded to one chloride. That's not how it works. It's a network. And so you'll have one sodium with 6 chlorides around it, and then a bunch of sodiums around those, and then a bunch of chlorides around those, and it forms a solid crystal. Or if it's dissolved in a glass of water, it's not really sodium chloride anymore. It's independent sodium ions and independent chloride ions. And so let's see, where was I? Examples of covalent molecules. Well, I already put a couple up there. Water, hydrogen peroxide. Oops. We could have methanol. We could have ethanol to disinfect our hands nowadays. And then examples of ionic compounds would be things like sodium chloride for flavoring our food, potassium chloride, copper bromide, and there are literally dozens and dozens and dozens of these in the homework for you to name. All right, now, in terms of the chemistry here, we need to be able to look at a substance, look at a compound, and know right away, does it have ionic bonding or covalent bonding? And a lot of you probably learned in high school about electronegativity. Well, we don't talk about that till quite a bit later. And you learned about difference in electronegativity and how you could, if the difference was this big, then it was ionic. If it's smaller than that, it's covalent and shared. I don't think that's a good way to do it. Actually, you can see that there's a better way to predict whether a substance is going to have ionic bonding or covalent bonding. It's much, much, much simpler, right? Because we don't have a table of electronegativities in front of us. And it actually works at least as good as the electronegativity method. And so what we're going to use is that if we have a covalent compound, or if we see a compound and it has a nonmetal plus another nonmetal, that means it's going to be covalent. And that will give us the right answer just as often, if not more often, than electronegativity differences. And then for ionic, it's going to be a metal plus a nonmetal. And sure, there are exceptions to this, but it will give the right answer just as often, if not more often, than electronegativity differences. And all you got to do is look at the periodic table. So that's a lot easier, isn't it? Okay, so now let's find the next page. Aha, on the handout, a periodic table. So we did this the other day, and we talked about nonmetals over here. And these are all metals. And so we can just look at the periodic table and see if it's one of these with one of those, it's ionic. If it's two of these together, it's covalent. Fantastic, right? Now, we pulled hydrogen out of here, right? And we set hydrogen off by itself. And for bonding, if that's in something, it's covalent, okay, not ionic. And then the first thing we'll do when we look at a compound for naming is we'll figure out, is it ionic or covalent? So we kind of got to know that. Now, what about all these in-between ones or some of these down here? Well, I'm not going to do that to you. That would be ridiculous, right? I'm not a psychopath, not a lunatic, okay? It's going to be very clear what you've got. Um, and then we need to know, based on where the elements are in the periodic table, if they're in an ionic compound, what charge does the ion have? What charge would it have? And that's where these group numbers are really nice. The 1A, 2A, 3A, all the way up through, 8A. Those aren't the official IUPAC numbers anymore. That's this 1 through 18. But, anybody who teaches chemistry still likes these old designations because they tell us, that 8 electrons, we'll learn all about that later, the octet rule and things like that. But they tell us where we are in terms of the charge. So if we have an element in this group, group 1A, and if it's in an ionic compound, well, it's a metal, so it has to be, right? +1. And then group 2, it's going to always form a +2 charge in an ionic compound. And then this will make it so much easier to explain this once we do electron configurations and we talk about the noble gas, all this stuff we learn later on in chapter towards the end of the semester. But for now, we're just going to memorize it. We don't have to know why or understand it. We'll just memorize it. We're going off of this noble gas group, which those don't form ions. And so we're going to go off of that and back this way. And group 7 is going to be -1. Group 6 is -2. So these are anions, -3. And then the group 3 and group 4 are kind of problematic. Your book, a lot of books say, well, you're taking, the group number and subtracting 8 or whatever. I don't know. That doesn't really work for me because group 4, these don't form ionic compound, carbon. That doesn't really work. Well, if you get down here, lead, tin, those don't act like, they don't always have the same charge, okay? They're going to act more like transition metals, even though, technically they're in this group. They act like transition metals. So there's no rule for group 4. None of those are going to be in ionic compounds that we will know the charge on the metal based on it. Carbon, silicon don't do that. So there's no rule for group 4. And then the rule for group 3, well, we would think it's +3, right? But boron, it's right on this border. Boron's going to be a non-metal. It's not even like a metalloid in here. It's going to form covalent compounds. And aluminum is really the only one then where the rule applies. Aluminum is always +3. And the ones below it, those are again like transition metals where they can have various charges. So we need to know what charges the ions can have. Group 1's +1, group 2's +2, the halogens, group 7 -1, then oxygen, everything below it -2, nitrogen, everything below it -3, and then aluminum's +3. All right, so I mentioned a little bit about transition metals. If you remember, transition metals are these ones, right, across here. And again, this makes more sense later on when we talk about electronic configurations, but these have more variability in them because of the electrons that they have available. We could talk about d orbitals and stuff, but again, that's later on. We're just memorizing this for now to get started. So transition metals can have different charges in different compounds, okay? So we can't look at what metal it is and know what its charge is. We have to look at what it is in the compound it's in. So we can't memorize it here. We just have to figure out. So these have various charges, and it depends on what they're in. So for instance, I don't know if you can see it here. Let's zoom. What the heck? Of course, now I gotta focus. Well, that's not working. Sorry. Bad production qualities. Iron. Iron can be +3. It can be +2. Cobalt can be +2, +3. Nickel, chromium can be +2, +3, all the way crazy crazy oxidation states. Now, there is one other thing, and this works better when I can see you in person and you can see the look of exasperation on my face. There's a couple of things that we're expected to know, and I think they're stupid. And, and I'm going to tell you, I think they're stupid. But every Gen Chem book has this. And that is that zinc and silver are exceptions. And this drives me crazy. But so transition metals can have various charges, but zinc is always going to be a +2, and we're expected to know that zinc is +2 in compounds, and silver is +1, and those are our exceptions. It's kind of like, rules in grammar that there's always exceptions. So the rule is transition metals can have various charges depending on what compound they're in, but zinc and silver are exceptions to that. Zinc's always +2 and silver is always +1, and we have to know that. Now, why did I say that that I think it's ridiculous or stupid? The reason is because silver isn't actually always +1. There's a +2 silver, and my guess is that this is something that has gone down through the decades, and it's just stuck in the Gen Chem books, and enough old teachers haven't died off. I don't understand it. I'd like to get rid of it, but I have not been elected emperor of the chemistry world, and so we're stuck with it, and we have to know those exceptions. You can probably forget them after Gen Chem class, but I have to be a responsible teacher and include them, as much as I hate that. All right, so next slide. What were we on? Naming. So why all that about what charges they have? So when you do this, when you do the homework, I want you to have this handout in front of you, and answer them with the handout, and then put the handout away after a while. So in naming, there's two systems. There's a system for covalent compounds and the system for ionic compounds. So this handout, it's very, very condensed. In the book, it's, all written out, right, in a lot of detail. But this is the process of naming. So when you're given a compound, the first thing you do is you ask, is it ionic or covalent? Right? And if it's covalent, you follow this system. Completely different system. So in the covalent system, you use prefixes to indicate the number of each element in the compound. So if there's 1, it's mono, 2 is di, 3 tri, 4 tetra, 5 penta, 6 hexa. And you got to memorize these prefixes, which ones they go with. Hopefully not too bad, right? Triangle, pentagon, hexagon, you've seen those before. Mono. Okay, so if it's ionic, there's also two systems. Okay, and so when you look at it, you first say, is it ionic or covalent? If it's covalent, I'll go this way. If it's ionic, I'll go this way. And if you have a metal that always has the same charge when it's a cation, then we don't use a Roman numeral. So that means if it's like in group 1A, they're always +1, like sodium. we can't use Roman numeral. Now, again, that's kind of dumb, right? Why would it be wrong to include the extra information? That's just the way it is. I can't change it. You know, if I were the emperor, we would just put a Roman numeral on every metal. Who cares, right? But by doing that, you're demonstrating that you know that sodium's +1 no matter what. And so then it doesn't get a Roman numeral. I guess that's the thinking. For compounds where the metal can have different cations with different charges. So what are those ones? Those are the transition metals. So the question really is, are they main group metals? Then you don't use a Roman numeral. If they're transition metals, then you have to use a Roman numeral to indicate the charge. So the example, iron can be +2 sometimes, it can be +3 sometimes, depending on what compound it's in. And then this part is something that you'll just have to get used to. It's true for both covalent and ionic. The second element in the chemical name has IDE ending. So you just change it from, if oxygen's the second element, you change it to oxide. If chlorine's the second element, you change it to chloride. Now, how do you know which is the second element? Well, it's the one closest to the upper right, closest to fluorine, but the truth is you don't actually have to know that, right? You're always either given the name or the formula, and the elements are going to be listed in the same order, right? So you don't have to know that rule that the second one is the most electronegative one, because we haven't talked about electronegativity, and we won't until what, November, right? And so yeah, it's the one farthest to the right and up is second, but you don't need to know that. The compound has it listed in that order anyway. So here's the other, there's a few things that I'm going to ask you to memorize to do some of this naming, because we are going to have some compounds with what are called polyatomic ions. And I'll do some examples, and hopefully it'll make more sense from the examples. But polyatomic ions are things that are covalently bonded, but they're ions, so they're in ionic compounds. So ammonium, this first one, NH4 plus, has 4 hydrogens covalently bonded to the nitrogen, but then the whole thing all together has a +1 charge, so it's an ion. And it can do just like sodium or potassium, it acts just like those in compounds, right? It can form a compound with chloride or fluoride and so on. And so that's what these are. They're covalent, basically molecules with a charge on them. So they're molecular ions. And they can form then, and do form, ionic compounds. Now, some of you, depending on your high school chemistry class, already memorized a whole bunch of these. A lot more than this. In some cases, I've talked to students that had to know a lot more than this. These are the 8 that I think are most important for us to know. So they can be tricky, right? Nitrate, nitrite, one difference in oxygen. But these are the most, so ammonium, nitrate, nitrite, sulfate, hydroxide, phosphate, carbonate, and cyanide. So you have to be able to write this and know the charge and recognize it. This might be the case where, you know, practicing with flashcards or whatever just to memorize them is helpful. And then, you know, there's a couple chapters on acids and bases in second semester Gen Chem, but these are important compounds, so we're going to have to know the common names for a few of the common acids, just these 4. But I just want you to know they're a little trickier than they might seem, right? And so make sure you're careful to memorize these and their formulas, because, you know, phosphoric acid is H3PO4. In your Coca-Cola, if you drink Coca-Cola. I think I'm running out of ink here. But H3PO3, that looks awfully similar, doesn't it? One oxygen different. It's not the same compound. And then you see how tricky this could be. HNO2, nitrous oxide rather than nitric oxide. We don't have to know those ones, but you see how easy it would be to confuse the formulas. So just kind of a heads up there as your chemistry coach. And then this next slide, you'll have to click on this since I'm doing this where I'm writing on the slides. See, I've got the handouts posted as always, and you'll just have to click on it to see. But I find this absolutely hilarious. So I think you should just go to read the Wikipedia page on this and see kind of the history of it. But it's a very, very long running scam where people would play on people's fear of chemicals and call up official people like mayor or a governor or something like that and warn them of all the dangers of dihydrogen monoxide. You know, it causes more deaths than any other chemical, which of course is true because of drownings. It's water. But so the DHMO hoax, as they called it, is really hilarious. And I just, you know, one of you might be governor of South Dakota someday, and I don't want you to fall for this. So, so read that just for a little bit of fun. And then the next thing is we've got these examples. So this is the handout, but I will do, you know, each of these individually and kind of walk you through the process. I don't usually do all of these in class because we don't have time, but we do have time on here, and if you want to skip over them, that's fine, right? If you've got the naming system down, you don't have to go through all of them. So let's do a few of them. All right, so CaCl2. So given the structure, given the formula, can we come up with the name? And so this is where you pause the video, right? And then do it, right? And then come back and see whether you got it right. So the first question from that handout, where was that handout again? I threw it on the floor as I get done. So the first thing we do is we go, all right, is it ionic or covalent? Well, ionic or covalent? Well, I gotta get the autofocus off. That's messing things up. Well, we've got a metal. Calcium's in group 2, so that's a metal with a non-metal. So we know that a metal plus a non-metal is always ionic. So we've answered that question. And then, so that's calcium is a metal, chlorine's a non-metal. And then the next question, what was the next question on there? Let's see. We have to know, does this metal always have the same charge when it's a cation? Or can it form cations with different charges in different substances? Well, let's see. Calcium is in group 2. Group 2A. And we know that group 2A is always +2 in compounds, right? When it's an ion, it's +2. So that means it does not get a Roman numeral. And in fact, it will be counted wrong if it has a Roman numeral, even though that's silly, right? But that's chemistry. All right, so the name of this would be calcium, just in the same order as the compound, and then chloride. And we know that there's +2 charge on that, -1 charge on that. And so the ending of chlorine goes to IDE. So, and there's no designation that there's 2 of them or anything like that, right? We have to just know that because we know how it goes together. We can't include that extra information. So what's the next one? Looks like it's the iron chloride. All right, I already gave it away, iron chloride. Aha, but it's more than that, right? So first question, pause it, answer it yourself, come back. All right, you got it? Is it ionic or covalent? Well, it's ionic because we have a metal plus a non-metal. Iron is a metal. And then iron, if you look at the periodic table, iron is a transition metal. And because it's a transition metal, and it's not one of those exception, it needs a Roman numeral. And that Roman numeral gives us the charge. So it indicates the charge on that cation. And so what is the charge? Well, we don't know. Right? We've got FeCl3, and we can't tell from the iron. We have to go back and look at the chloride. So the chlorine is in group 7A, and group 7A is -1 always in ionic compounds. Now don't get confused, chlorine can be in covalent compounds too, then it can do anything under the sun, right? But if it's an ionic compound, chlorine is always -1 because it's in group 7. So if chlorine is -1, what does iron have to be to make this thing? See, there's no charge on that, right? There's no charge indicated. So there's 3 chlorides that are -1. Does it make sense to you that iron has to be a +3? Right? Because you've got 3 chlorides. That's what that compound is. So the name for it is iron. And then we indicate that +3 with a Roman numeral 3 and then chloride. All right. Should I do all of these in one take? I told you I wasn't going to be recording any more 50-minute suckers, but let's see what the next one is. PCl3. Okay. So again, first question is always, is it ionic or covalent? And looking at the periodic table, you'll find that phosphorus and chlorine are both nonmetals. So a nonmetal with a nonmetal is covalent bonding, right? And that means we're going to use that other system. Where's that handout? We're going to use the prefixes, right? And so we have to memorize those prefixes. And again, the elements are in the same order. Can I spell phosphorus? I can't if I'm at the board. Something about being at the board, I usually get it right, but I'm always nervous. But I cheated and wrote it out ahead of time. Phosphorus. Doesn't look right, does it? But I think that's right. So phosphorus. Now, why don't I have a mono in front of it? That's one of those goofy things, right? I hate this stuff. Sorry to, all this stuff that makes chemistry hard, right? It turns out that the rule is we do not use mono for the first element. In other words, if there's only one of the first element, we leave the mono off. It's assumed that there's only one of them. Why would they do that to us? Why would they care if we actually stuck it on there? I don't know. That's just the way it is. I apologize based on chemistry. But that's just what it is. So instead of monophosphorus, it's just phosphorus. And then there's 3 chlorides, so it's going to be trichloride. Phosphorus trichloride. All right, do we have another one? What's our next one? Is it I think, yep, I've got another well, I don't want to give it away, another covalent one. But yeah, 2 nonmetals. So that's covalent. And the prefix for 2 is di, so we're going to have dinitrogen. And then 4 is tetra, so we would think it's tetraoxide. But for some of these, when there's 2 vowels together, they will get rid of the vowel and just go tetroxide. And then other ones, they'll go tetraoxide. Here's the deal. I don't care if you know which one's right. I'm not going to do that to you. I'm not a lunatic. Right now, I don't remember which is right myself. There's a confession for you, because it's not a good, it's a rule that is not followed. It's like different for different ones. So if that's the case, then why should we worry about it, right? This isn't even as good as I before E, except after C. Uh, so anyway, hope that's okay. I'm an irresponsible chemistry professor. Let's see, one more. This one I'm sure you can do now that we've done those other ones. So we're going to look at it again, have to answer ionic or covalent. And like I said, I normally would not do all of these in class because everybody gets so incredibly bored. And here it is, it's 10 times more boring on this, right? But you can stop it and walk away. Actually, you can do that in class too, but never mind. So if you need more help, they're here, or once you've got it, you just click it off and you're done. So ionic or covalent, well, potassium, that's a metal. So if it's got a metal, it's ionic, right? Metal plus non-metal. And then what metal is it? Well, that one's going to be in group 1A, and group 1A is always +1, so that means no Roman numeral. And so this one would just be potassium fluoride. Now, when you do it on the computer, this is I don't even want to tell you what the common misspelling of this is, but it's very common, and the computer is going to count it wrong, right? It's going to count it wrong if you spell it fluoride. So just kind of pay attention. What you want to do on the homework is go through it once and double check everything, and then just use it for practice, because once you've got the points in there, it doesn't matter. You can make mistakes on them and it won't count off, right? You've already got the points on the board. Okay, so last one on the list, I believe. And so we look at it again, and we've got 2 nonmetals. And so it's going to be prefixes. And we don't put the mono in front of the first element, but the second one we do. Now here's one where hopefully it really makes sense. We wouldn't go mono oxide, right? That would just be awkward. So it's going to be carbon monoxide. And of course, you've heard of carbon monoxide poisoning. Hopefully you've got carbon monoxide detectors at home. All right, so that's the naming. I think I did all of them. Yep. And so I will do some other examples with polyatomic ions and things like that maybe are a little bit more challenging, but I will post those separately. All right. Thanks, everyone. We'll see you next time.